Hello class, in this video we are going to look at this problem regarding the coincidence of shared birthdays. We have 5 parts to complete. Let's look at the part A. If 2 people are selected at random, the probability that they do not have the same birthday is the multiplication of those 2 fractions. Explain why this is so. Ignore leap years and assume 365 days in a year. The first person can't have any birthday, so they can have a birthday on 365 days. In order for the second person to not have the same birthday, they must have one of the 364 remaining birthdays. Okay, because the first person already taken a spot, the second person can't, because we do not want them to have the same birthday, because we are looking for the probability they do not have the same birthday, right? And so that's part A, pretty simple. Part B, if 6 people are selected at random, find the probability that they all have different birthdays. Okay, the probability that they all have different birthdays is round to 3 decimal places. I'm going to show you how we find the denominator and the numerator, okay? So consider 6 people. We consider 6 time slots or 6 days. We want to choose the birthday for the 6 people. The first person could be any day, right? And the second person also could be any of the 365 days. The denominator would be 365 to the power of 10. Okay, I don't have my writing pad today with me. So knowing the denominator is going to be 365 to the power of 6. Denominator is going to be 365 to the power of 6. Numerator is going to be 365 times 364 times 363. You know, every time we multiply by a number, it's going to reduce by 1. So let me get my calculator here. If the part A makes sense to you, part B is just a generalization of part A. All right, I'm going to stop share that and then share my calculator. So basically, it is 300 in the denominator, as I said, is 365 to the power of 6. Numerator would be 365 times 364 times 363 times 362 times 361. 1, 2, 3, 4, 5. Okay, one more. 360. 1, 2, 3, 4, 5, 6. Basically, is a permutation of the 6 people in the 365 days of the year. 1, 2, 3, 4, 5, 6. And then divide that by 365 to the power of 6. The denominator is the total number of ways to arrange birthdays for the 6 people. If we see the experiment as arrange birthdays for the 6 people, and that is that. And we need a decimal, right? So let's see how do we round it. It says round to 3 decimal places as needed. 3 decimal places. So it's gonna be 0.960 because 5 is bigger than or equal to 5. 960. Let me enter that. Point Oh, it's decimal, so we don't need it. It's fraction. Get rid of that. 0.960. Right? Part C. If 6 people are selected at random, find the probability that at least 2 of them have the same birthday. At least 2 of them have the same birthday is a very complicated situation. It could be exactly 2 people have the same birthdays, or exactly 3 people have the same birthdays, or exactly 4 people have the same birthdays, and so on. And let's say exactly 2 people have the same birthday. The 2 people could be the first 2 people, or any 2 people of the 6, right? So it's very complicated. When that happens, we want to find the probability of the complement and use 1 to minus the complement. Let's consider the complement of at least 2 people have the same birthday among the 6 people. Do you agree the complement of at least 2 people have the same birthday among the 6 people is none of them have the same birthday, or the 6 people all have different birthdays. So basically, part B is a complement of part C. Part C is a complement of part B. So in order to find the probability in part C, we can just use 1 to minus the result we got from part B, round to 3 decimal places. It doesn't say use the result from the previous problem. Let's see if we can just use that rounding from earlier. That will be the 0.140, because they should add up to 1, right? No, 0.4, my gosh, 0.40. 0.040, right? Their complement. Part D, if 22 people are selected at random, find the probability that at least 2 of them have the same birthday. Well, at least, so we want to use the same strategy. We find the opposite, we find the complement, and find the probability and use 1 to minus. The probability that at least 2 of the 22 people have the same birthday would be 1 minus the probability of all the 22 people have different birthdays. Okay, so I'm gonna use calculator. Let's go to the calculator. 22 people, just remember. Okay, so we're gonna have a very complicated numerator that we wanna arrange the 22 people in 22 different days among the 365 days. So that's actually 365. Go to math, probability, NPR. Among the 365 days, we're going to choose 22 days to 22 different days and then arrange the 22 people there, right? So that's the numerator. And then we need to divide that by 365 to the power of 22. Okay, looks good. And that's the probability. And then use 1 to minus that. Ignore the sign because we switched the order. So the answer is going to be that. Let's see what's the rounding. Still going to be round to 3 decimal places. So 0.476. 0.476. 476. Right? Part E, the last one. Show that if 23 people are selected at random, the probability that at least 2 of them have the same birthday is greater than half. Just do the same thing with earlier, right? In part D, we have 22 people. In part E, we're gonna, have 23 people. And we wanna know the probability that at least 2 of them have the same birthday. Okay, we're gonna go back to calculator again. This time, we're gonna use P365 23, right? 365, and go to math, probability, NPR, 23 people, 23. Close that, that's the numerator, and divide that by denominator is 365 to the power of 23. Close that. That probability is shy half, right? So we should be able to answer that. If we keep two decimal places, it's going to be 0.493. The probability of none of them, sorry. So at least two have the same birthday. Then probability of none of them have the same birthday, we're going to use 1 to minus that. Ignore the sign. So 507 is 507.507. That is yeah. The probability that, okay, let me stop the sharing and then go to the Pearson again. So the probability that none of the 23 people have the same birthday, we got it from the calculator, is 1 minus at least 2 have the same birthday, is 0.507. The probability that at least 2 of 23 people have the same birthday is, oh, okay, we got that in the calculator. It's going to be 0.493. 493. Let me double check the rounding. Yeah, 493. The probability that 3 exists. Oh, sorry. The probability that there exists people with the same birthday is, then the probability of not sharing birthday. Big is smaller. That at least have the same birthday. Exist the same birthday is smaller than the probability of 23 not sharing a birthday. Okay, let me sort it. So we got none of them have the same birthday is, oh, I messed up. This is none of them have the same birthday is 0.493. This is that. None of them have the same birthday, 493. And this one is 0.507. Double check. Yeah. So the probability that there exists people with the same birthday is bigger than the probability that, okay. Yeah, that's what it means when the class size, like you go to university and you have class in different, you have different classes, right, the semester. If the class size is bigger, if the class size is bigger than 23, you will see the chance of having at least 2 people have the same birthday is bigger than none of them have the same birthday. Right? So that's everything for this problem. Hopefully it's clear.